Okay, so today we're going to be going over the Arrhenius equation. The Arrhenius equation is one of the most important and underlying equations within physical chemistry because it forms a relationship between rates of reaction and its dependency on temperature. And this was the goal of the Swedish chemist savant Arrhenius when he tried to come up with this equation. And as I'm sure many of you are familiar, the equation is given as K equals A times E to the power negative EA over RT. Now let's go over and dissect this equation bit by bit, starting with the first variable, K. Now K, as you might have been familiar with before, is denoted as the rate constant. And this rate constant doesn't have a fixed unit, and why is that? Well, we've known from previous understanding that rates of reaction are given as the rate constant multiplied by the concentration of reactants. Say we had one reactant A, and its relative order of reaction. We don't know this order of reaction. It could be any number technically, so we'll just denote it as n. If we had a second reactant, say B, same would be applicable. Now the reason it doesn't have a set unit is because it depends on the order of reaction, the integer order of reaction of these reactants. We know that rates of reaction are given as concentration per time. This is usually denoted as moles per dm cubed seconds. We also know that concentrations are given as moles per dm cubed. Now say if we had a total order of reaction of 1, meaning that we added the coefficients of each of these reactants together, and it came out as 1. We had order of reaction of 1. Well, if we were to try to find K, we would divide rates of reaction by these relative concentrations, giving us moles per dm cubed seconds over moles per dm cubed. Now, canceling these out means that our rate constant has a unit of seconds to the power negative 1, or per second. In this case, it would be that, but if we say had order of reaction of 2, the same would not be applicable. So let's move over to the next variable, which is A. This is denoted as the pre-exponential factor. Now that's just jargon for a constant. It's a constant that alters depending on whatever reaction you're undergoing and the temperature at which that reaction is taking place. And this is just a measure of the likelihood that collisions are going to occur within the reactants in your reaction, and the likelihood that an actual successful reaction is going to occur, meaning that a product is formed. And we're going to go over this in more detail later on. Now this whole chunk here, e to the power negative e a over RT. E is just Euler's number, but this whole chunk is very important because it allows us to visualize the impact that temperature has on our rate constant, and from this statement here, its impact that it will have on our total rates of reaction. And how does it do that? Well, we can see a relationship here between e to the power negative EA over RT. EA is given as activation energy. Now we are quite familiar with this. It's the minimum amount of energy required for two colliding reactants to have a successful reaction or forming a product. R is just our universal gas constant. It's a constant in itself. Temperature is our absolute temperature given in Kelvin. And so if we rearrange this, if we used indice laws to rearrange this, could turn into 1 over E to the power negative EA over RT. And this could then turn into 1 over E to the power EA to the root of RT. And from this, we can visualize a relationship. We can see that as T increases, we are square rooting this to a larger power, to a larger root, meaning this will be smaller in general, and that this whole chunk will give us a larger number, meaning that our rates of reaction will be higher. And this can actually be visualized when we see one of the most common relationships formed from the Arrhenius equation, and this is the relationship between the rate constant and temperature. So rate constant was given as K, and we have our temperature here, an absolute temperature, Kelvin. This actually forms an exponential relationship, and the reason that it does form an exponential relationship and say not a linear relationship or the alike is because of that previously described logarithmic relationship where we have E, Euler's number, and its indice, meaning that it does form an exponentially increasing relationship between K and temperature. Now, the way that K actually increases with temperature varies between reaction to reaction and depends on the reactants occurring. Say if the reaction was slower, then the change would be smaller, whereas if the reaction was more volatile, if it occurred more readily, then this would be steeper by far. And another popular relationship that you probably have covered before would have been a logarithmic one. So let's take our Arrhenius equation. We know that K equals A times e to the power negative E A over RT. If we actually natural log both sides, we get ln K equals ln brackets A times e to the power negative E A over RT. Now using log rules, we know this equals ln K ln A plus ln e to the power negative EA over RT. Let's keep going. More log rules equals ln A minus EA over RT. And we know ln E is just the same as 1 because e to the power 1 is equal to E. So let's cancel this out. And from this we have ln K equals ln A minus EA over RT. Now if we actually plot this ln K to 1 over temperature, you might have seen this before, we get a linear relationship, a perfectly linear relationship. And why is that? Let's actually look at this expression here. We have ln K. We know K is our dependent variable, so let's denote it as y. ln K is just going to be a constant in the end. It's e to the power what equals K. So we have y equals ln A. ln A is unchanged. It's not going to vary with our independent or dependent variable, so it's just a constant. So we give it as C minus EA over RT. Now we can actually split EA over RT into negative EA over R multiplied by 1 over T. If we multiply the denominator together, we will just return to what we formerly had. And from this, we can isolate our independent variable temperature and what it's multiplied by. This constant, negative EA over R. It's still going to be a constant, so minus mx. It's very similar to the form of a linear curve. And from this, when we actually extrapolate points on this linear line to ln K and 1 over T, we can actually figure out what our activation energy is. And the reason for this is we have 1 over T, this is our x-axis, this is how it's going to change with temperature. We have ln K, this is how it's going to change with our y-axis. What we don't know is m. M in y equals C minus mx is going to be the gradient of our curve. So if we find 2 points, if we find ln K and we get 1 over temperature, we can substitute these into the equation, we can substitute these values to find the gradient of our line, and the gradient of our line is going to equal to negative EA over R. Therefore, our activation energy is going to be the gradient of our line multiplied by the universal gas constant, which is just in the end a constant. It's just approximately 8.314. Now we're going to go on to something else. Something that was formulated after the original publication of the Arrhenius equation. This is the modified Arrhenius equation. Now we know that our original Arrhenius equation is given as K equals A times e to the power negative E A over RT. Now our modified Arrhenius equation is useful because it's slightly more accurate, and the reason of this is because of here, our pre-exponential factor. The modified equation is given as K equals capital A times T N times e to the power negative E A over RT. Now in wider literature you may see this represented as A T N EXP brackets negative E A over RT, and you don't have to worry about that. EXP is just another way of writing e to the power of whatever is in the bracket. So from this we can see that we no longer have a pre-exponential factor. Instead we have A multiplied by T to the N, and this is because of the intrinsic way that we actually calculate our exponential factor. Our exponential factor A is given as Z multiplied by this P shape, which is the Greek letter rho. What these actually mean is Z is denoted as the collision factor, whereas rho is denoted as the steric factor. Our collision factor, as it's eponymously named, is just the likelihood that our reactant molecules are going to collide within our reaction. And so this is intricately linked into our actual pre-exponential factor, as I previously mentioned, how likely it is for the reaction to occur and the rate at which it does. Whereas our steric factor is the likelihood that collisions will occur with the proper orientation, and that's how we get our pre-exponential factor. Now, this steric factor is actually quite difficult to calculate with modern technology. So what we actually do to calculate our steric factor most of the time is to empirically deduce A, our pre-exponential factor, and Z, our collision factor, and from that, rearrange this to find our steric factor as A over Z. And now, the reason that we have our modified Arrhenius equation in the first place is because A, our pre-exponential factor, is directly linked with changes in temperature, and the reason of this is because of Z, our collision factor. Our collision factor, as we know, is quite self-explanatory going to change with temperature. As temperature increases, our reacting molecules move faster, they're more likely to collide, therefore they're more likely to have successful collisions. Therefore, we can infer that A has a direct correlation with temperature. However, when we use our previous Arrhenius equation, let's actually derive this. You may have seen this equation before. ln brackets K2 over K1 equals negative EA over R brackets 1 over T2 minus 1 over T1. Let's actually derive this. We have our first equation here. Let's take our logarithmic one. Let's take our logarithmic equation. We have ln K1, our first rate constant value, equals ln A minus EA over RT1, our first temperature value. And we also have ln K2 equals ln A minus EA over RT2. This is our first equation, this is our second equation. Now we can actually rearrange our first equation to make ln A the subject. We have ln A equals ln K1 plus EA over RT1. Substituting this into our second equation gives us ln K2 equals ln K1 plus EA over RT1 minus EA over RT2. Now let's rearrange this. ln K2 minus ln K1 equals EA over RT1 minus EA over RT2. Therefore, ln brackets K2 over K1 log rules equals, now let's isolate EA over R, EA over R bracket negative EA over R, sorry, as we are so familiar with this expression, 1 over T2 minus 1 over T1. Now this is also a very familiar equation, and it's widely used within the Arrhenius equation because it's just a rearranging of two possible scenarios. Two possible scenarios that come as a result of two different temperatures corresponding to two different rate constants. And from this, when we looked at our previous graph of our linear line of ln K to 1 over temperature, if we extrapolated these points and got values for K1 and temperature that we can find, what we can actually do is work out our activation energy. When we sub in two different temperature values and two different rate constant values that correspond to those two temperature values, we can just sub them in, rearrange, and we can find our activation energy. But how can we do this? We just found out that A, our pre-exponential factor, alters with temperature. If A, our pre-exponential factor, alters with temperature, now how can we assume that everything else is the same when temperature varies, and that we'll get the proper activation energy for a reaction when we sub in these different values? Now this is actually one of the shortcomings of the Arrhenius equation where it doesn't incorporate this. It's an assumption. It doesn't incorporate this into its calculations, which is why the modified Arrhenius equation, where direct relationship between a pre-exponential factor and temperature is first used to find our rate constants before anything else is done. And this is why it's modified, and this is why it's more accurate. However, when we're using this equation that we derived at the bottom, we notice that the pre-exponential factor doesn't change much. It's not a large it doesn't play a large role in making our results inaccurate. And the reason for this is that our pre-exponential factor actually alters only by a very minute amount over a very small change in temperature. Obviously, as the difference in temperature increases, this difference will increase as well. However, when we're trying to find the difference between rate constants between two very similar temperatures, which is what we often try to do, then this will be directly applicable, because we can assume that our pre-exponential factor doesn't change by a large margin, and therefore our calculations and our results are still applicable and verifiable.